Today we are going to cover a really interesting topic around Kubernetes. In this chapter we will talk about Kubernetes resources like CPU and memory, what are requests and limits, and how those are managed internally in a Kubernetes cluster. We will also give you some tips and tricks to help you guarantee stability, reliability, performance, and cost savings. Let's go for it. Let's start talking about the Kubernetes Scheduler. The Kube Scheduler is the default scheduler in a Kubernetes cluster. It runs as a part of the control plane, and it determines which nodes are valid placements for those pods that are waiting in the scheduling queue. It ranks valid nodes based on the available resources and other constraints, and eventually will bind every pod on the nodes with the highest score. We can break down this process into two different steps: filtering and scoring. During the filtering process, the Kube Scheduler filters at the nodes with enough resources to satisfy the request from a pod. Filtering produces a list that might contain multiple candidate nodes to handle the pod, or this list might be empty if there is not any node at that moment that can satisfy such requests. On the other hand, scoring is the process where the Kube Scheduler scores every node on that list of candidates. The node with the highest score will be the best option for the Kube Scheduler to run a pod. As soon as there is a node elected through the mechanisms that we just described, which are filtering and scoring, the Kube Scheduler will communicate its decision to the Kube API service. This is done by just updating the pod definition through the Kube API service. And the way it works is quite simple. The Kube API service notifies the kubelet running on the elected node. As soon as the kubelet sees that it has a new pod scheduled on the node, it will create and run the pod's containers. But what happens if there is not enough room to allocate this new pod in the cluster? The Kubernetes Scheduler will try to preempt any low priority pods to make it possible to schedule this new pod in the cluster, assuming that this new pod has a higher priority. Another way of evicting pods is when the node is under pressure. We will see this in detail later, but basically the way it works is the kubelet is permanently trying to be below certain threshold. As soon as the kubelet sees that this threshold has been surpassed, the kubelet will try to bring back some resources. To do that, it will start evicting pods, but these pods will be evicted following certain order. To determine the pod eviction order, it will use three different parameters. The first one is whether the pod resource usage is exceeding the pod defined requests. The second one are the pod priority classes. And the third one is the pod resource usage relative to requests. There are also quality of service classes to classify pods based on requests and limits. These quality of service classes can help the Kubernetes Scheduler to make decisions on which pods should be evicted first in case of node pressure. Now it's time to talk about Kubernetes resources, like CPU and memory. In Kubernetes, CPU is measured in CPU units. That means that one Kubernetes CPU is equivalent to one either physical or virtual CPU. It will depend on the server architecture. You can also specify fractions. That means that one Kubernetes CPU is equivalent to 1000 millicores. Or the other way around, you can say that 100 millicores is equivalent to 0.1 cores. Memory is measured in bytes. So if you set 1G, you actually will be setting 1 gigabyte. The same way, if you set 128 Ms, you actually will be setting 128 megabytes. Requests are resources Kubernetes allocates when a container is created. We could say that this is the initial number that a container is granted and guaranteed to use. From a general standpoint, request is the way the Kube Scheduler calculates whether a pod can be scheduled in a Kubernetes node or not. When the total amount of resources requested by all the pods running in a Kubernetes node exceeds the total amount of resources on that node, no more pods will be scheduled on that node. When scheduling a pod, if there is not any Kubernetes node with available resources to allocate the initial request, this pod will remain in a pending state. However, a container can use more resources than those initially requested, but this will only happen when there is enough resources available in the node. Let's dig deeper on how CPU requests are managed underneath. Kubernetes relies on Cgroups, being more specific on CPU shares and the CFS, which stands for the Completely Fair Scheduler. That basically means that every process and thread in a container will run in a specific cgroup for the container. CFS is responsible for providing CPU resources to that cgroup. CFS doesn't understand CPU Kubernetes units. It operates with CPU shares, which is no other thing than CPU time. So we need first to understand how to convert these CPU Kubernetes units to CPU shares. To make it simple, we could say that one Kubernetes CPU, it will be equivalent to allocating CPU time for one whole CPU, or what's the same, we will be allocating 1024 shares. That way, if a container is requesting for one CPU, it actually will be requesting for 1024 shares. Similarly, in a container that is requesting for 500 millicores, it will be actually requesting 512 CPU shares underneath. Let's see how it works in a real example. Cgroup management begins with the root cgroup at the top level, which holds the 100% of the CPU time or 1024 shares. From this cgroup, the CPU time is split into three different cgroups: system slice, user slice, and kubepod slice. System slice is the default cgroup that will hold the resources for running systemd services. User slice is the cgroup that will hold resources for every user in the operating system. And kubepod slice is the cgroup that will hold the resources for every pod running in the Kubernetes cluster. In this case, so far, CPU time is equally divided. Each cgroup has 1024 CPU shares, or what's the same, each cgroup will hold up to 33% of CPU time, if all cgroups are demanding CPU shares simultaneously. From here, we can keep nesting cgroups by setting cgroups to new users with different weights, or by setting cgroups to pods running in our Kubernetes cluster. What is actually happening behind the scenes when requesting and limiting resources in Kubernetes. For those systems where the pods are most of the time idle, CPU shares will not play that fundamental role. That's because CFS use CPU shares to distribute and guarantee CPU time when a system is under heavy load or contention. Let's think of requests as a percentage of CPU time guaranteed for a specific CPU time period. For explaining this, we are going to use 100 millisecond CPU time period. For this example, let's set a half of a core or 512 CPU shares. For a CPU time period of 100 milliseconds, that means that we are going to use the half of the CPU time period, or 50 milliseconds. The same way, for a 100 millisecond CPU request, it will be guaranteed a tenth of a whole CPU time period, that is, 10 milliseconds for each 100 millisecond CPU time period. On the other hand, if there is no contention on the nodes and a pod needs more resources, it will be able to get more CPU time unless it hits its limits. Now we know how resources are granted and guaranteed in the case of contention on the Kubernetes nodes. If your workload requests are well-sized, CFS should guarantee enough CPU time for each cgroup. And remember, this is mainly important when the system is under a heavy load and there is competition for the CPU. So, if resources like CPU and memory are somehow guaranteed in the case of competition, why should I take care about limits? Let's see it. Limits defines the total amount of resources a container can use. We could say that is the ceiling for a container. Container can use more requests than those initially requested, but never can surpass the total amount of resources defined in limits. Earlier, when we talked about requests, we saw how cgroups guaranteed some specific amount of resources. This time, we will see how cgroups will limit the total amount of resources a container can use. Following the same principle we have been using earlier of 100 millisecond CPU time period, let's imagine that we want to set a new CPU limit in Kubernetes. Let's say, for example, that we want to set one CPU Kubernetes limit. In this case, the container will be allowed to use up to 100% of the CPU time for every 100 millisecond CPU time period. In a similar way, if we set a 200 millicore CPU limit, we'll be allowing to use up to 20% of every 100 millisecond CPU time period for that container. So limits are important if you want to avoid having containers using more resources than those initially expected, which might cause trouble, especially if requests and limits are not properly configured across your infrastructure. There are some situations where using Kubernetes limits can be beneficial for us. Let's enumerate some of these use cases. you may want to predict your workload usage on multi-tenant environments. So you can observe and monitor the resource usage of your applications, or you can avoid limits which will let the application use as much resources as they can. The latter approach will work until there is node contention, which may end up with unpredictable behavior. Second could be if you want to build resources to your customers. By setting limits, building resources to your customers will be much easier. And third could be workload design and QA. By setting limits, you will get better understanding on how to size your application properly, and whether your application is behaving properly in some situations. Now let's talk about what happens when a container hits one of its limits. In terms of CPU, CFS will throttle the threads in a cgroup. That doesn't necessarily mean that the process itself will be killed or stopped, not at all. The process will remain in a kind of pause state. That means that it will experience some delay in completing the whole task, since it requires more CPU time periods to process the whole task. When it comes to memory, when the container hits the memory limit, let's say that the process will not remain in a kind of pause state. The own killer will be invoked and will kill the container. This container will be recreated from scratch. If we want to get a better understanding on how Kubernetes schedules pods, we need to talk more in detail about pod priority and quality of service classes. Pod priority indicates the importance of a pod relative to other pods. The pod importance is key when scheduling new pods in a Kubernetes cluster. The way it works is simple. When scheduling new pods in a Kubernetes cluster, if there is no room for that new pod, the Kubernetes cluster will try to schedule this new pod by evicting pods with lower priority. That's what we know as Kubernetes preemption. In order to set pod priority to your pods, you first need to create a priority class. Once you have a priority class, then you need to set the priority class name parameter to your pod definition. Priority class defines the pod priority by using an integer value. The higher the value, the higher the pod priority. As soon as priority classes are set, pods with priority class on its definition will retrieve its priority value from there. At scheduling time, pods are ordered by priority, being scheduled pods with higher priority ahead of lower priority pods. Let's go now with a deep dive on QoS in Kubernetes. QoS stands for Quality of Service. Pods running in a Kubernetes cluster are classified and allocated into a specific QoS class. The way that Kubernetes allocates a specific pod into a specific QoS class is by evaluating its requests and how these requests are set relative to resource limits. Kubernetes QoS delimits different groups of pods. These groups will be evaluated and elected to be evicted from a node in the case that there is node pressure. QoS classes can be ordered by more likely to be evicted, as we will see now. In Kubernetes, there are three different QoS classes: guaranteed, burstable, and best effort. Let's talk about guaranteed. For a pod to be classified in the guaranteed QoS, it has to meet the following criteria. First, for every container in a pod, it has to have set limits and requests for both memory and CPU. Second, for every container in a pod, limits need to be equal to requests for both memory and CPU. Pods in the guaranteed QoS have the strictest limit set. That means they will be less likely to be evicted. They are guaranteed not to be killed until they exceed their limits, or there are no other low priority pods in the node that can be killed first. Let's go with burstable. A pod will be in the burstable QoS class if this pod doesn't meet the criteria to be on the guaranteed QoS class, or at least there is one container that has a request or a limit for CPU or memory. Pods in the burstable QoS class are evicted only after pods in the best effort class, which is the QoS class that we will see next. And then we have the best effort class. Pods in the best effort class will be those pods that doesn't meet the criteria to belong to either the guaranteed QoS class or the burstable QoS class. Pods in the best effort class will be the pods more likely to be evicted when there is node pressure. So as you already saw, setting requests and limits is something to take into account, especially when the node is under pressure. Not only because we want to be sure that our pods have enough resources to keep running, but also because we want to understand how eviction priorities works when the node is under pressure. Before wrapping up, let's talk about why rightsizing your workloads is important. If you overprovision your Kubernetes clusters by assigning more resources than those really needed, you will be wasting money, since you will be reserving resources that will not be used eventually. On the other hand, if you underprovision your Kubernetes clusters by assigning less resources than those really required, you will put stability and reliability at risk, since applications might end up having to consume more resources than those really available on the nodes, and leading the kubelet to having to start evicting pods due to the node pressure. If we have to enumerate a few factors supporting why rightsizing workloads is key, we could say the following 3 factors: reliability, performance, and cost savings. In terms of reliability, as we introduced a few minutes ago, by sizing applications incorrectly, we can cause a lot of trouble. Reliability of your infrastructure will be at risk. When applications are permanently using more resources than those initially requested, we can say that applications are not well configured. We will be allowing the Kubernetes Scheduler to allocate more pods than those it could really handle. On the other hand, by setting very high limits, or even missing those limits, we will allow compromised containers or buggy software to start consuming resources until leading the node to resource starvation. In terms of performance, we could say that the same reliability principles can apply to this. If requests are not configured or are too low, containers could try to use more resources. This is something that you should expect, since containers are allowed to use more resources than those initially requested whenever the limit is not surpassed if configured and there are enough available resources on the node. But in the event of missing container limits, or when those limits are too broad, CFS via Cgroups can begin waiting and throttling CPU time on the node because of a resource competition on the node. Containers competing for CPU time can keep running, but some delays could be expected, and even some errors at the application layer. On the other hand, if we are too conservative by setting lower limits than real application requirements, we will not put at risk the node stability, but we could compromise the pod performance. CPU throttling, or even worse, the pod could be killed by the AMP killer. And last but not least, the third factor that supports workload rightsizing is cost savings. By requesting too many resources without control, we are reserving resources that will not be used in the future. So we will be charged and we will be paying for something that we are not going to use eventually. It is absolutely recommended to take a look and closely monitor the actual and real usage of resources over the time. You will have a better understanding not only on how your application is performing, but also what are the times where your applications are consuming more resources. Correlate that performance data from your infrastructure with your requests and limits information from your containers. That way, you can figure out whether you are well sized or you need to rightsize. If you see that your actual resource usage is below your request and there is still margin to reduce those requests, you could save money. If your actual resource usage is too far above request, try to accommodate and set a proper value to avoid node pressure scenarios. In terms of limits, try to set limits according to your needs. Too high limits could end up in node starvation. On the other hand, too low limits could lead to problems on your workloads. Hey folks, this came to an end. If you like it, please click on like, and if you want to keep updated on what's coming next, you can click on subscribe. So, see you next time. Cheers!